Example, f is a function in R2, two variables. This function we encountered previously, fxy is 1, 0, xy is 0, xy is not 0. Then we know that the partial derivative of f at 0 is 0. Why this is 0? By definition, this is the limit of t goes to 0. f 0, 0 plus t e1. e1 is 1, 0. Maybe I will write it here. No, I don't want to write it here. So this is, what's this? This is t, 0. Okay? Minus the value of f at 0, 0 divided by t. So this is 0 because both the two f here are all 0 because one of the variable is 0. But if one of the variable is 0, then the value of a function is 1. Therefore, these two terms are 1. So 1 minus 1 is 0. So this is 0 divided by t and take limit. Of course, the limit is 0. Similarly, you will see that the partial derivative of f with respect to y at the origin is also 0. Consequently, the partial derivative exists. In other words, the gradient of f exists. Of course, the gradient is also 0, 0. But f is not continuous. At 0, 0, right? Because the value of f on the coordinate axis is 1. Outside the coordinate axis, the value is 0. So it is easy to see that f is discontinuous at this point, 0, 0. Because very close to this point, the value of f is 1. There are also points where the value of f is 0. So f could not be continuous at the origin. And since f is not continuous, f must not differentiable. At the origin. Okay, so partial derivatives, both partial derivatives exist, could not obtain the differentiability of f at that point. This is quite different from single variable function. In the study of single variable calculus, we know that f is differentiable at the point if and only if the f is derivative. F have derivative at that point. Okay, that's for single variable functions. But for multi-variable functions, this is no longer true. Okay, so the existence of partial derivative could not ensure differentiability. This example shows that existence of partial derivative does not imply differentiability. Okay, but if we strengthen the conditions slightly, we require a little more than the existence of a partial derivative. We will regain the differentiability. Okay, so this is our next theorem. Suppose f defined near the point A have all its first order partial derivatives at every point. All point x in this neighborhood. Remember this situation? The partial derivative of f at the point A can exist or not exist. But here, this condition not only requires the partial derivative at the point A exists, we also require that the partial derivative exists at all x. Okay? For every x in the R neighborhood of A, f has all partial derivative at x. Okay, this is what we required. So we have partial derivative functions. This partial derivative become a function defined in BRA for any I. So if all partial derivative for all I, for all x, if for all I, all x, this partial derivative exists, then for every I, we let x change, we obtain a new function. We denote it by DIF. This is the partial derivative function. We introduced the partial derivative functions in the last lecture. Okay. So this partial derivative function can be continuous or not. It can be continuous at A and not continuous in other point. Okay. So our conclusion is that if all this DIF is continuous at the point A, then f is differentiable at A. Okay, so here we have to consider partial derivative not only on A, not only at A, but also at nearby points for every x in the neighborhood of A. If all these partial derivative exist for every x, we obtain the partial derivative function defined near A. Well, if this partial derivative function is continued at A, then our function f, our original function f, is continuous, is differentiable. Okay, so this is the content of our theorem, very important theorem, and now we will prove this theorem. To prove this theorem, because for the simplicity of notation, we prove for two-dimensional case. In two dimension, x1, x2, we denote by xy. Okay. So the proof of this theorem, we consider two-dimensional case. Then assume A is x0, y0, and f, the partial derivative, if the partial derivative with respect to x and with respect to y, this is defined in the neighborhood. These are defined in the neighborhood of A, that is x0, y0, and by our assumption, these two partial derivative functions are continuous at A. Okay, so what can we what should we obtain? To study, we want to prove that f is differentiable. F is differentiable. Our purpose is differentiability. To study differentiability, we need to consider the change of the value of the function. So we need to consider this. In the two-dimensional case, our h we use KL. Okay, actually I can be used KL. No. H can also use two components. Okay, so this A plus H, you consider H is KL. Then FA plus H minus FA is F. A plus H is X0 plus K Y0 plus L minus F X0 Y0. Okay, so this is a X0 Y0 and this is the R. We consider a small rectangle. This is, here is a X0 plus K. Here is Y0. Here is X0 Y0 plus L. Of course, this is X0 plus K Y0 plus L. Okay, so we want to study the difference of the value of this function at the center of this disk and at this point. How to study this? We write this in this form: fx0 plus ky0 plus l minus f x0 y0 plus l, and we add it back again: x0 y0 plus l minus fx0 y0. We add a point, we add a term and subtract that term, and then we group this together. Okay, our difference here can be written to be the sum of these two. And for the first term, we consider this function. Maybe we study the second will be